Hi everyone, so we're going to look at the types of substances revision sheet now. So here are all the specification points. There's quite a lot in here, and actually going through this revision sheet we probably are not going to cover every single specification point, so it might be still worth looking at some of them. So for example, the properties of fullerenes and polythene, for example, and there won't be covered from what we're going to discuss shortly. Okay, so we are going to fill in this summary table about some different substances and structures that we've been talking about over the last few revision sheets. We haven't done all of them before. We have been through ionic and simple covalent. We haven't got an individual video about giant covalent and metallic bonding, but we'll go through that now. Okay, let's start off with ionic bonding. So structure and bonding summary. So my key point with ionic bonding is that it's between a metal and a non-metal. So metal plus non-metal. That is opposed to simple molecular covalent bonding models, which are all between non-metals. Okay. Similarly, because this is covalent bonding as well, this is between non-metals, and metallic bonding is just between atoms of metals. Okay, so that's a key thing. So the summary of ionic bonding, if we think back to our revision sheet from before, it's where you gain or lose electrons. So then you have a charge, atoms or ions, and then those charges have an electrostatic attraction. So plus attracted to minus. And it forms a lattice structure. So we've drawn this previously. I'm just going to do a quick example here. So we've done a plus and a minus and a plus, where they're attracted to each other like that. We can also represent it as something like Na plus Cl minus. Okay, like that as well. We can also draw them out as well. So I might look at my periodic table. I might have lithium chloride, for example. So lithium is in group 1. It can lose 1 electron. We'll have 3 in total. So I do Li, I circle around. So it's lost an electron, so it's become positive. And then my chlorine, which has 7 electrons in the outer shell. I'm just checking this. Chlorine, there you go. It's got 7 electrons in the outer shell. So 1, 2, 3, 4, 5, 6, 7. And it's gained an electron from the lithium. So it's negatively charged. I guess actually technically, if I'm putting a dot there for lithium, this lithium atom should be with dots, just to show where that's come from. So that's another way to draw it. So key properties. So it's got a high melting point, MP for melting point, high boiling point, soluble in water, because it forms ions, conducts electricity in water, in solution, or as a liquid, but not as a solid. That's because the ions can't move in a solid, whereas they can in a liquid or when they're in solution in water, so mixed in with water. If you have things that are able to move, that means that or ions that are able to move, or electrons that can move, that means it will conduct electricity. Next one, simple molecular covalence between non-metals. So that's where they share. Oh, trying to write share and pair in the same word, which is not working. Share pairs of electrons. And then they're generally small molecules. As we say, it's simple covalent. So we've drawn that out before. So for example, we could have oxygen, which is O2. It's got O here for oxygen. Oh, didn't mean to hit the camera there. So that shares 2 pairs of electrons because there are 6 electrons in the outer shell for oxygen. So they need to make up 8, so they share 2. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I can also represent that by O and O with 2 lines in between like that. Okay, so they generally have a low melting point, a low boiling point. Some are soluble in water. And most don't conduct electricity. That's that one. So giant covalent structure, these are examples, would be diamond, graphite, which is what you get in your pencil, what we commonly call lead. It's not actually lead, it's graphite. So non-metals, bonding between non-metals, and again, similar to the simple molecular covalent structures because they are covalent, we're sharing pairs of electrons. But they're not small molecule. These can have billions of atoms, and they're found in a lattice structure. Okay, so you could have graphite, which kind of looks a bit like this. I'm going to attempt to draw it. So each of these dots represents a carbon atom. And they come in kind of layers. For graphite, these layers can slide over one another, which makes graphite really handy for pencil. So we've got a layer here of graphite and a layer here. So that one is diamond. This one is graphite. And then in between these layers, you've got weak forces between them. So between the layers. Which means that the top layer can slide with respect to the bottom layer. You don't have that in diamond. You can see they're all attached in there, which makes diamond really, really, really strong. Okay, so in terms of melting points, it's got a high melting point, high boiling point. They're insoluble in water, so they don't dissolve in water. Most don't conduct electricity, except carbon as graphite. So graphite does conduct electricity. Okay, there we go. And then metallic bonding is the last one. That's between metals. So you have electrostatic attraction between the metal ions, which are positive because they lose electrons, and the delocalized electrons, which are negative. And we can show this by a little diagram that looks a bit like this. So each of these circles represent our positive metal ion. And then we have these dots represent the delocalized electrons. So these electrons can move from one direction or another, which means they conduct electricity. So if we look at this, they have a high melting point, a high boiling point. They're insoluble in water and they conduct electricity in their solid and liquid form. So there we go. I've summarised that. Like I said, it's not covering every single point in here, but we're covering quite a large majority of it. There we go.